Is it visible at the moment?
Yes, sir. It's visible.
Okay, so a very good evening to all, and hopefully, if there is someone from abroad, then there may be different time zones. So, the title of my interaction with you is Advanced Power Electronic Interface for Energy Vectors. Actually, this term energy vectors was being used in one of our proposals, so I picked up that thing. But while just going through the slides, I was wondering that basically we consider energy to be a scalar quantity. So in what respect it becomes a vector quantity? This term has been is evolved on the basis that um, when we consider that there is a transfer of energy from let's say any location to a different location, or and even in respect of time, if we are trying to visualize the thing, it becomes a vector quantity. So energy with which is, let's say, being generated somewhere in some remote location can be taken out in this city. So at what time and what position is it from that origin? That's what is making it a vector quantity. And most of the time we consider the form of electrical energy directly associated with this energy vectors, where there may be different forms of energy. It may be some sort of conventional energy sources like fossil fuels or thermal power plants, the hydropower plants, things like that. And the upcoming this renewable energy technologies, everything may be taken in the same group. Even we can also include various type of storage systems under the same energy vectors. So initially I planned to cover a wide range of topics, but then later on I realized that it will become quite lengthy one. So at the moment I'm just trying to focus one aspect of energy vector that we have recently completed in our research group, and that is more related with wind power kind of applications. So I think the slide should move. Yeah. So if we think in respect of the wind energy capacity, so we'll find that in recent years, since let's say 2013 to 2022, in respect of global capacity and annual addition. So global capacities are highlighted in yellow color, and annual additions are being highlighted in green color. There is a tremendous jump in wind energy, and not only wind, rather I should also include photovoltaics, because in our country we are doing really nice in photovoltaics area. But for today's talk, I just picked up one section that is more related with wind energy. So a typical wind energy looks something like this, where we can have both the solutions like doubly fed induction generators or permanent magnet synchronous generator. So both the options are there. With the DFIG, we know there are some limitation in respect of our reactive power or magnetizing energy that is required by the induction generator. However, with the PMSG, we don't require that kind of energy, so we are not going to unnecessarily load the transmission lines with that kind of energy. So straightforward, we can have a very simple solution like PMSG, which where we require full rated AC to DC rectifiers, and then there is some energy storage DC link, and then back to DC to AC. And then we can go into some sort of three-phase AC. And this AC may be somewhat both, it may be a standalone system, like we can put it into some standalone microgrids, etc., or we can also place it somewhere on a realistic grid connected systems. So in this case, the conventional system suggests that there may be two stages of power electronics getting involved. One is when we convert AC into DC, and then DC to AC, along with some energy storage. So for last couple of years, we are trying to look into some other possibilities where we can directly move into AC to AC configurations for taking out power from the wind turbines. And for this, various kind of proposals have been given by researchers in past several years. And if you look into the classification of these AC to AC converters, we can group into different categories. So it may be some converters with the DC link storage that may include some solid state transformers, some sort of converters with DC link, or there may be some DC link with current kind of configuration where the interfacing is in respect of current. Broadly, there is involvement of high inductances there. The second category may be matrix converter, where we can think about some direct matrix converter or indirect matrix converters. And in this category, for the indirect matrix converter, we can have some conventional possibilities, then a sparse matrix converter is there, ultra sparse, very sparse. These most of these matrix related work has been done by ETH Zurich group, in which Professor Kolar is there. His group has contributed a lot onto the development of various type of matrix converters. Apart from that, there is another group in which hybrid matrix converters have been reported, and in this category there may be some sort of hybrid direct power converters, some integrated this impedance source network within the matrix converter, and even we can have some Z source type of matrix converters. So currently we are trying to explore this hybrid arrangement in our group. Just you can stop me anytime if you have some questions to ask. I'll try to answer them during the presentation itself. So about the matrix converter, this is the conventional direct matrix converter. So you can see there are three phases that are coming from the input side, which are represented like small ABC. And there is a section that is going into the load section that is represented by capital ABC. So in each of these phases, we have bidirectional switches. So basically, these are bidirectional control switches. And if you look at these symbols, the schematic shows that there may be two sort of IGBTs which may be connected back to back in such a manner that one of them IGBT conducts at any time and the remaining current is taken by a diode, or vice versa. So it's going to take care of both positive polarity and the negative polarity. So this is going to happen when all the three phases, and that leads to this kind of direct matrix converter. The second category of the matrix converter is indirect matrix converter, where there is basically a kind of a two-stage solution, but you may consider it as one single stage as well. So in this case, there may be some current source rectifier CSR that has been shown in this figure for the IMC, indirect matrix converter. And the second section is the voltage source inverter. So you'll find that in between this looks very similar like what we generally see around as a back-to-back connected converters, where one stage is our rectifier stage and the other stage is our inverter stage. And this is commonly being used in a number of applications. However, you will also appreciate one thing, that there is no DC link capacitor that is sitting in between the rectifier stage and the inverter stage. So the absence of these capacitors actually helps us in miniaturizing the converter size. Because in the conventional converters, primarily there were two stages. So the rectifier stage was developed separately and the inverter stage was developed separately. However, in this arrangement, we can put all the semiconductors within one single package, and that will bring down the size of the indirect matrix converter. So this is another approach, and it is this is what we actually picked up in our research group, and we started exploring the potential of indirect matrix converters. So apart from indirect matrix converter, there were also some sort of matrix converter that were being reported. One is what we call as a sparse matrix converter. The second is known as very sparse matrix converter. And the third one is known as ultra sparse matrix converter. So there are different types of matrix converter, and all these falls in the category of indirect matrix converter. So you may say this is a sub-classification of indirect matrix converter. Interestingly, what you'll figure out is that the evolution of these matrix converter from DMC to IMC, further to SMC, VSMC, and USMC, the entire evolution has considered the number of transistors and the number of diodes as their first priority. So with all these sort of evolution, efforts have been made to reduce the number of devices, particularly semiconductor devices. So the number of devices in both DMC and IMC are same. However, in SMC and VSMC, it is further coming down. However, there is one issue that must be mentioned here, that is the number of diodes are getting increased. So in VSMC in particular, the diodes has becoming tremendously very large. On the other side, the ultra sparse matrix converter that has the least number of transistors, with 9 transistors in it, and there are around 18 diodes. So these number of diodes are quite similar what we were getting in DMC and IMC. However, the number of devices, switching devices, are coming down, and this is the way in which USMC is represented, where we have got these diodes, and in each leg we have got only one switch at a time. So basically, with the presence of this diode, it makes this particular type of device as a bidirectional device, and we have one switch to control it. So this is what, for what reason we have started looking into USMC in more detail, so that we can take out the benefits of USMC. At this stage, I must mention one limitation of USMC. That is, it is a unidirectional kind of converter. So most of the time, what we refer in respect of unidirectional is power can be transferred from, let's say, from the source towards the load side, but the other way it's not possible. The control power cannot be done. However, in form of for braking and other purpose, some amount of power can be transferred back into the supply side. So controlling these USMC has always been a big challenge for all of us. The only reported technique that is actually quite popular as on date is what we refer as a space vector modulation. So apart from this, there were other techniques also being proposed earlier. They were based on some sort of algorithms, etc. However, their dependency on some kind of time varying quantities were there, and that make it less popular. In this case, with the SVM, we are able to allow it for better utilization. In respect, I hope some of you might have done the space vector modulation. Even for the inverter also, if you have done it, you will be able to appreciate this work. So we can utilize this in a better way in respect of the vectors. So SVM actually controls both the magnitude and the of the output voltage as well as the input power factor. However, sorry, placement. However, the way in which this switching scheme is decided, it's slightly important to understand that what makes it interesting that we don't need any DC link capacitor, because in most of the cases you can see that anything which is going wrong on the rectifier side if is absorbed by a DC link capacitor. However, in this case there is no DC link capacitor. So if there is any modulation related issues, that will directly reflect onto the next stage, that is your voltage source inverter. So we need to be very careful in respect of coordination in between the CSR stage and the voltage source inverter stage. So for the CSR, we make use of the current source vectors. So in this case, these currents like IAC, IBC, all these sectors are being decided. So we just like established space vector modulation, here we consider the hexagon and we put all these current vectors along the 6 sides of the hexagon. And the reference current vector is actually taken in respect of the 2 adjacent vectors or phasors of the other 2 currents, and later on the duty ratio is being decided. So there is some sort of relation, mathematical relation, that is generally being implemented in the digital controllers, where we make use of these duty ratios and modulation indexes, and this is some sort of template. You can see the alpha angle is what is very important in this case, which actually decides in which particular this sector it will lie. Just a phone call is coming. Okay, so sorry. So this is a few of the things about USMC, and then for the USMC, the CSR stage switching sequence is presented something like this table here. That is when we are moving from the various phases AB, AC, AA, back to AC and AB. So different duty ratios are assigned to each of these phasor quantities. Likewise, there is also an involvement of 0 vector terms in between, and that decides whole of the switching duration. So this is for sector 1. If we want to move from sector 1 to sector 2, then we have to redefine the angles alpha such that we can go into the next sector. Likewise, we can just keep on shifting the alpha angle, and the rest of the approaches are same, except that we all the time we generally make use of the 2 adjacent vectors at a time. However, we can also think about considering 3 vectors at a time for some specific purpose to generate kind of a rotating phasor quantity. So this is the CSR section. Likewise, we can also do the space vector for voltage source inverter. There is some typo over here. It should be a space vector diagram for voltage source inverter. CSR should not be here. So this is our voltage source inverter, which is feeding some 3-phase loads. And here we can make use of the adjacent voltage phasors to decide in which particular sector is it lying. So it is an analogy just similar like our current phasors, except that it becomes a voltage quantity at the next stage. So CSR takes the entire phasor in respect of current, and VSI takes it in the form of voltage. And here again, you can see within the same switching duration, there are different duty ratios assigned to different vectors. So if we are right now we are showing that there is a reference vector somewhere in between V1 and V2. So we are making use of the duty ratio corresponding to V1 and V2, and then the zero vectors are helping us to decide how much is the overall length of the rotating vector. So if we are adopting whole of the length of this V2 and V1, it will be the kind of modulation index will be at its maximum value. If we want to reduce modulation index further, we need to make use of the zero vectors. So these are some of the mathematical expression in respect of all these quantities. Further, when we want to combine, because right now we are not using any capacitor in between, so that means there is some sort of synchronization or coordination that is required in between the CSR stage SVM and the VSI stage SVM. So while we are making a coordination in between these two, the straightforward method is to take a product of these two quantities. So here you can see in the bottom side the duty ratios. Let's say in respect of D1, whatever has been written is a product of DIAB times of DV1. Likewise, D2 is decided by the product of DIAB times of DV2. So we are basically considering these vectors together, and we are making a product of these two quantities on instantaneous basis, and that makes it more difficult to handle. So while implementing this type of scheme, sometimes we did encounter issues related to electromagnetic switching noise, which was creating some sort of problem in synchronizing the two switching schemes together. Now, in our work, basically this was done by one of my PhD scholar. His name is Vallabhbhai Seva. So he completed his thesis on this specific topic, and currently he is working with a Japanese company called TMEIC, which is actually located in Bangalore. So he did really nice work, but his approach was to look into some realistic problem that is somewhat related with the AC drive application. Now with the AC drive application, there we make use of AC to AC converters. And in that case, the common mode voltage is considered to be a serious problem. This actually leads to some sort of bearing current in the machine, and this current which flows through the bearing section, in long run it creates a problem for the bearing of the machine. So this may be seen in various type of machine, but it is actually present in induction machines also. But for PM machine, it becomes more disastrous because we are making a very expensive machine and its bearing is getting failed. So 50% of the motor failures are generally accounted for by the bearing failures. This high frequency bearing current, which actually is a reflection of the PWM switching of the inverters, creates bearing current to flow through the bearing, and that actually heats up the insulation that is kept in the bearings. And with time, the insulation gets heated up, and further its life gets shortened. So in this work, primarily, this was a big limitation. Apart from that, the voltage gain of the USMC is only 0.866. So we can say it basically reduces the output voltage as compared to your input voltage. So that is another limitation. And on the other side, if you look in respect of the load power factor angles, the operating range is limited in between -30 degree to 30 degree. So load power factor angle operating range is more related with the input power factor, So if we want to operate the input power factor close to unity, up to maximum, we can make the load power factor angle vary between -30 to 30 degrees. So that was a serious limitation for USMC, because you'll find that the load power factor angle with some of the machines goes beyond this range. So it becomes difficult for the converter to handle this one. So before I move on to this topic in further, if you have any questions or comments, then you can ask it. Okay, so it seems there are no questions at all. So that's good. Okay, so let's move on with this slideshow. So for the physical understanding of the common mode voltage, basically this voltage is which actually arises somewhere in between the neutral of the machine with respect to the physical ground of the three-phase supply system. So this VCMV has been represented here, and this gets a path through which actually the PWM, what we call it, the bearing current flows into the physical ground, and that is a path which is not directly linked with the converter operation, but certainly it actually activates number of capacitors which are surrounding the converter. So these capacitors provide a path, and that path gets completed in these local loops. So we can, for a balanced load, generally what we say that a sum of all the three-phase voltages are equals to 0, and correspondingly our common mode voltage also comes out to be 0. But under the unbalanced situation, the situation is a bit different. So in this case, the CMV variations can also be seen when we are trying to look in respect of the normalized input phase voltages. So there is some region in which the difference can be seen, and this is what is actually resulting into some sort of CMV energy content or CMV values. So VSI sectors, you can see in the during the 0 states, in particular, the value of these peak CMV for the CSR is going up to 0.866, and for V7 it is going up to VM peak. Likewise for the 246 CR, so that is corresponding to the switches which are getting activated in that particular mode. And for the active vectors, certainly the amount of CMV is less. So somewhere we are getting the issue of CMV more aggravated because of the presence of 0 vectors, and that's very obvious because 0 vectors actually creates a sudden dip in the voltage. So for this, what we thought of that we can add few more 0 vectors in such a way that the transitions may be avoided. That is, when there is a certain change in the voltage from very high value to 0 value, that may be kept at its, so that transition should be kept at the minimum values. So what we did was we added these 0 vectors. Generally, we have a kind of a predefined 0 vectors in the VSI stage, and what we say is all the high switches getting on or all the low switches getting on creates a 0 vector. But in this case, what we did was we also created one additional 0 vectors by making use of some auxiliary shoot-through switches. So these switches, if you look at these switches, they are actually placed in between these two points where the switch S4, S5, and S6, they are actually taking it to some different levels. The main idea was that the peak transition of CMV that was happening during zero vectors can be shifted to some other zero vectors. So this is we achieved by using these active AST switches that is coming across the output filter. And these are a few of the switching sequences. Further, there are different modes of operation. So if you start with the PNN state, so how the CSR and VSI stages are getting connected. So effectively, we can say this VPQ is actually our DC link voltage. Pseudo DC link voltage. There is no capacitor actually, but there is a ripple type of voltage VPQ that is can be seen there. For us, the more sensitive matter was in respect of the CMV. So in different stages, you can see that the amount of peak CMV is getting changed. So it is peak CMV is VM by root 3. Again, it's VM by root 3 in both these two stages. Further, it is becoming 0. So for us, our main concern was how to restrict the peak CMV. So some of the simulations were being done for some specific conditions. So those parameters have been listed here for where the input is 325 volts, 50 hertz, and output load frequency is 100 hertz. So we are thinking of increasing the operating frequency of the converter from 50 hertz to 100 hertz. Typical load power is around 2.5 kilowatts and 5 kilohertz of switching. So if we look at the CMV's values, we can see that the amount of CMV is changing in a wider range. So it is going from, let's say, around minus 325 to plus 325. So that is what we could get in the simulation, that VCMV max was going up to 325 volts. Later on, apart from this CMV, we also actually monitored some other parameters. So the DC link voltage, VPQ, has been shown as 485 volts. So this is it's not pure DC. It's a kind of a, you can say it's taking the upper levels of the AC sine waves, and in between there, the black color is showing that there is a high switching frequencies. So we were getting this kind of envelope, and when we take it so this is the DC link, and simultaneously the input is obviously a perfect sine wave. Onto the CMV side, this has already been shown here in this figure, and CMV in the proposed method was something like where we are trying to make use of the auxiliary shoot through states, and we are adding the what we newly framed zero vectors. So that actually helped us to reduce the common mode voltage from 325 volts to around 188 volts. So you can see that there was a tremendous difference in between the conventional SVM and the proposed method. That is where we are making use of the auxiliary shoot through newly created zero vectors. So that is the CMV problem is getting better. Further analysis are in respect of the amount of voltage that we are getting across the switches. So across the AST switches, certainly the voltage stress was getting up. So it has went up to around 563 volts. Likewise, the VSI switch voltage stress was also 563 volts. And by looking at the FFT spectrum, we can see that the blue one is a conventional Fourier transform in respect of the conventional SVM for USMC, and the red one is showing us the proposed one where we are actually adding the auxiliary shoot through created newly zero vectors. So there is a shift in the spectrum which is towards the higher frequency. So it is getting shifted to the order of difference, and overall the main idea was to take it slightly away from the lower frequency range, so that we could get by making use of this newly zero vectors. Further, the supply frequency was also changed, so we changed the AC input supply voltage, both voltage frequency from 50 Hertz to 100 Hertz, and this reflection was directly visible in CMV also, so it was also changing its frequency. When the load voltage, output voltage was being changed in respect of frequency, the CMV was not getting affected. So we can say that CMV was primarily governed by the amount of input supply frequency. The peak CMV, if we compare with respect to conventional and proposed, there is a big margin, and these values are independent of the modulation index. So that implies that even if we change the modulation index of the AC to AC converter, so this broadly remains fixed, but certainly the proposed one is giving us a better solution. These are few of the experimental results that were being obtained. So we could not test it at around 400 volts or so. There are two issues. The one issue is handling such voltage and current levels sometimes is a bit risky for the people who are working close to it, particularly a number of times because of some silly mistake, something goes wrong, then there are issues. Apart from that, the idea was just to confirm the concept. So we can also scale it down a little bit, and we can still get it done. So we could do the experiments at around 75 volts, 50 hertz, and correspondingly the DC link, which was VPQ in the previous slide, has gone up to around 104 volts. Onto the output side, we are getting around 50 volts of output, and the corresponding frequency was 100 hertz. So it shows that we are able to enhance the operating frequency. However, the overall voltage is getting reduced. So from 75 volt RMS, we are coming down to 50 volt RMS. Then comparing with the conventional modulation CMVs, where we are able to get around 193 volts, with the proposed method, this was coming down to around 116 volts. So this was one more figure of merit we could get from the proposed method. VSI output voltage seems slightly disturbing, particularly when we try to look into the effect of frequency. So CMV corresponding to 50 hertz and CMV corresponding to 100 hertz, there was not much difference in between the two. So with this approach, what we found that common mode voltage may be improved by adding a newly created zero vectors. However, the voltage gain is one problem, and then load power factor angle, operating range is another problem. So particularly the voltage gain was one serious problem, because we are able to get 50 volts RMS out of 75 volts. So we thought of improving it. For that, we have gone to the hybrid matrix converter, where we started making use of the quasi Z source USMC. So you can see the impedance network, which is nowadays being used in a number of high gain converters, was being used in this case as well. And there are different ways in which impedance network can be connected. One method is when we try to put the impedance network onto the supply side. The other approach is when we try to take it towards the DC link side. So both the approaches can be considered. There may be some differences, because if we are keeping it outside the semiconductor, then possibly on the supply side this may be a better solution. However, in our work we tried to take it inside the converter and we placed it somewhere in between at the DC link side. But certainly it's not just similar like your capacitor, which occupies a lot of space and has a limited lifetime as well. So this is the schematic of our work, where CSR and VSI were there, and in between we included one Z network, which is established quasi Z source arrangement. So we have got two inductances, in this case, two capacitance and a diode. So we have not used, some doubts are there. Anyone wants to ask some question? Is there anyone have any question? Because I don't know, I'm not able to hear anyone. If there are some questions, please do ask. Okay, hopefully I'm audible. Am I?
Yes, sir. Yes, sir. You are audible, sir. There's no question from audience side.
Okay. Thank you. So, so now, interestingly, this Z network, it hasn't got any switch. So, primarily, what we did was, this is one impedance network, and we are making use of the switching of these switches so that we can bring down the shoot-through state to these impedance network. So there are two stages. One is the non-shoot-through mode, and the other is the shoot-through mode. So with the shoot-through mode, primarily what we do is we try to store the energy in the inductors. So the moment when we are doing the shoot-through implies that we are short-circuiting two switches together. Let's say if we are short-circuiting or we are closing the switch G1 and G4, so we are going to create this kind of shoot-through. So there will be no power that is getting transferred to the load side, rather it remains confined into the DC link. So, and further, the energy storage elements actually gets charged. So our inductor capacitor is getting one path. The second section is where we have one more current that may also flow through. I think here there is some confusion. I'm not sure about the diode orientation. So possibly there is one more path that energizes. I think I have some doubt with the diode representation here. It should be solid or dark or light. So basically the idea is that during shoot through we can charge these passive elements, and during non-shoot through state the energy of these passive elements can be transferred into the load side. So that's how we can lift up the voltage level. So the expression of different voltage are here, and the final expression I'll just like to share with you is this Vp dash Q dash is represented as 1 upon 1 minus twice dst times of Vpq. So where is Vpq? Vpq is somewhere here, which is actually acting like an input for this impedance section, and Vp dash Q dash is the output of the impedance network. So depending upon the shoot through period, we can have different values of Vp dash Q dash, and we can, but whatever value it's going to come. Any doubts, please? So whatever value of Vp dst is going to come in picture, so it will try to increase the it will try to reduce the denominator term, or indirectly you can say it will provide some gain factor to this output voltage. So by making use of this concept, the voltage gain was being done. So this is a few of the things in respect of the CSR and VSI. So there is not much change, except that we are introducing the shoot through period within the same sequence. So DST, which is the shoot through period, is well taken in this case, and we have to follow one condition that says that the summation of our modulation, overall modulation index, which is a product of the current modulation and the voltage modulation, and sum of DST should always be lesser than equal to unity. This is one mandatory condition to ensure that THD of the output voltage is not getting bad. So so making use of this, we can get kind of a magnified or higher output from the converter. And these are few of the design equations that were being derived for calculating the values. So this is our we can just quickly look at how the non-shoot through and shoot through states are actually distributed onto the converter side. So this is one section of that TS/2 timing period when we are considering the current source rectifier phasors IAB and IAC, and correspondingly we are also referring to the voltage source inverter timing sectors, which has been shown here. So out of the whole section, some section has been dedicated to shoot through, and the remaining section has been utilized for the non-shoot through period. That is what is also restricting M plus DS lesser than equal to unity factor. So again, we also looked into the peak CMV in this case also, and the idea was to just keep an eye on the peak CMV. Now, the issue that we could figure out was, in this case, certainly there is a presence of zero vectors, so CMV is getting increased, and apart from that, the total shoot-through mode in one place leads to more ripples in the inductor current. So the second point is really interesting because that gave us another idea that if we are trying to place the shoot-through states carefully, then we can also regulate the ripples in the inductor current. So you can see this is the nature of the inductor current that is flowing through the converter, because you have inductances in the Z network as well. So right now we are looking at that particular inductor. So this peak value of the inductor current, you can see there are different values like A/2, then B/2, C/2, and so and so. So it just shows that the maximum amount of ripple is actually somewhere in between this A/2 factor. Which gives, so accordingly we have to go for the design of this one. So this was happening with unequal shoot-through durations, and these are our simulation results. In this case, you can see the CMV is also getting improved from 356 volt to 238 volt, and the line-to-line voltage is coming out to be around, but the main transition line is around 250 volt. The main transition that is happening is you can look at the delta IL value. So in the conventional case, the delta IL, that is the current ripple, was going up to 6.36 amps, but simply by reassigning the shoot-through states, we could bring it down to around 4.83 amps. So this was a marginal improvement, but still it was noticeable that we are getting some benefit in respect of current ripple. And you can see the green ones, the current ripple before 0.05 time seconds are of the order of 6.36, and after that instant it's getting improved. So we try to compare the conventional and the proposed method, that is where we are trying to take care of the inductor current ripples, and this peak CMV was actually getting improved in this case as well as compared to the conventional. But not only the peak CMV, rather we are also getting a benefit in respect of maximum inductor current ripple. So the inductor current ripple with the conventional one was much larger as compared to the proposed one, and this we are just simply doing it by reassigning or reallocating the position of the shoot-through states. And further, as a function of shoot through, this is just showing the overall gain of the converter. So we can when we are saying overall gain, it means we are looking at the final output, and that's our overall gain. So we can get a huge jump, but primarily as a function of M plus D factor. So M plus D factor must be kept lesser than equal to unity. So overall gain is quite large. So these are few of the experimental results. You can see 50 volt, 50 hertz, and then 72.5 volts for our DC link. The inductor current was around 4 amps, and this is 138 volts of VP dash Q dash. So you can see the difference. VPQ was 72.5 volts. VP dash Q dash is 138 volts. So there is a jump in the impedance network output voltage. So then the moment we change the modulation scheme, so there was much benefit. So this boosted voltage proposed. So this value was not getting increased too much, but the current ripples were coming down. So 2.8 amps of current we were getting. So again, if we compare the CMV factor also, it is 178 volts over here, and with the proposed one, it's coming down to 110 volts. And output voltage, okay, this is what we expected to give us. So we could get around 60 volts of output at 100 hertz. Now you can see the input was 50 volts, 50 hertz, and the output we are getting is 60 volt, 100 hertz. So that means now we are moving towards an idea where both frequency can also be changed in a wider range up to around 100 hertz or even higher than that we tried. And apart from that, the voltage was also getting increased from 50 volt to 60 volt. But there were few limitations with this one. With the QZS USMC, we were using around 4 passive elements and a diode. You can think about 2 inductor, 2 capacitor, and a diode. And the moment when we go into high power applications, these passive elements creates or it actually increases the size of the converter, which is actually a big trouble with the matrix converter, where size, we always try to reduce the size of the converter. So in the next we also looked into some other alternative options. Apart from QZS approach, we also tried with switch boost USMC approach. In this case, the impedance network got changed. The rest of the things are as such. And then we place the shoot-through states in predefined manner. So this is our switching sequence. So during shoot-through states, these are the modes of operation. During non-shoot-through state, we are getting some. So this approach is the same. The only thing that there is some change in the equivalent circuit, but primarily the shoot-through is being created by shorting the 2 switches in one single leg. So overall, we are gaining some boosting factor, and here the boosting factor is represented as so B is equals to under root 3m by 2, 1 upon 1 minus 2 DST. So this factor is getting changed, and accordingly our output voltage is also getting changed as a function of peak voltage. These are some of the design equations which we calculated for the L and C values, and further therefore a few more equations. Going into quickly into the simulation results. So these are some of the simulation result in respect of the switch boost converter. So you can see the CSR boosted voltage. So these things are there. VPQ we are getting is 149 volts. VP dash Q dash is 372 volts. So we can see there is a big jump in between the input and the output of the impedance network, and that carry forwards to the next stage of the AC voltage levels as well. So in this case, we placed a 46 volt 50 hertz supply, and these are few of the results for the stresses across various devices, and this is our switch voltage and inductor. So so let's say if we are talking about the load voltage, now we are jumping from 46 volts to 70 volts, 100 hertz. So that is further taking the gain to a higher side, and we are also getting a benefit in respect of lesser amount of the stresses across the devices. One more benefit we could figure out of this SB USMC was we can have some unbalance in the supply voltage up to, let's say, plus minus 10%. However, with the switching scheme only, with the modulation scheme, we can remove this unbalance. So even if your input voltage is getting unbalanced, output voltage becomes balanced. And that is the beauty of the SVM being applied to this type of matrix converter. So these are few of the more results. That is when we are looking at the supply voltage 60 hertz, then output voltage becoming 50 hertz, few more results, efficiency were being compared, and there were few comparisons. And if you look at the last, this SB USMC proposal, so if we are making our overall gain up to 2.5, so we can make it more consistent. And it is of the order of, let's say, around close to 90%, not exactly, but let's say close to the 90%, particularly when we are working at low power levels. In this case also, we try to reduce the CMV using similar approaches which we actually used earlier. In this case, we are dependent upon this VCMV as given as VB plus VP dash Q dash. And further, there were a few more things which we did. So I quickly want to go on to some of the results. Simulation results are there. So 149 volts we are getting for the DC link here. Okay, the ratings were not strictly the same. We managed to these values at different levels. Ideally, they should be same, but we could not do it. Sometimes because of some circuit-related issues, we take it to some different values. So reduction in peak CMV with these CMV of the proposed method, we could reduce it by around 20%. Few more results, that is hardware results. So 50 volt, 50 hertz, we are jumping to 75 volt, 50 hertz. So we have particularly for drive application, this sounds really nice. And this may be quite useful, and the idea behind entire this work was not only to look in respect of CMV, but other performance parameter, let's say in terms of voltage gain or in terms of inductor current, ripples, etc. So primarily this is all about the topic that I thought of sharing with you, and I'll be more than happy to answer your questions if there are any. Thank you. A few people are there to listen to me.
Sir, myself, Nikita Prajapati. I want to ask one question, sir. Sir, how will decide the grid parameter and which grid parameter will be taken for the grid, and how will decide the range of grid parameter for microgrid system?
When you say grid parameter, so are you strictly looking at one specific value or number of values?
The number of values.
So for the grid parameters, I think there are some predefined standards that is well given in IEEE standard, among IEEE standards. But I'll say that let's say if what thing is more important for you so when you want to bring down a number of let's say renewable systems with the conventional grid, so you are always concerned about your phase sequence, your frequency match, your voltage match. These things are well established. So you need to just look at the grid values. Now, how you are saying, because grid can have different levels. So at what level are you looking at the distribution network, or are you looking at the transmission side? They have different...
So distribution network.
So for distribution network, you can think about the three-phase supply system within, let's say, even in your campus of MMM UT, typically, let's say 415 volts, 400 volt system is there for the distribution side. So that may be one sequence. Frequency, you don't vary a lot. So let's say very limited range is there for frequency mismatch. And apart from voltage and frequency and phase sequence, these are the three critical things to consider when you are bringing down your solar or the renewable sources on grid. So, okay, from power electronic perspective, we do talk about harmonics issues, that harmonics should be lesser than 5%, or even individual harmonics should be lesser than 3%, something like that. So there is IEEE 519 that actually predefines it, but you can refer to some standards. I don't know whether I have answered your question or not. If there are some more, you please ask.
Thank you, sir.
So if there are any other questions, please. You can also ask question not directly related with the talk. If you have some other thoughts in mind, we can also interact on those questions, and I'll try to answer them as much as I can.
Sir, there in question chat box, they have asked about your reference paperwork to share it.
Okay, so if you want to see the reference paper, then I say that you can directly go on to the, I hope my screen is visible to you all. So you can directly go on to the IIT BHU website, and I think generally I put everything there. So within that box, just hold on. So electrical engineering, and in this one you can look at the faculty. Inside the faculty you can look at me, and in this I have some details that is given on my website. So publications are listed there. If you go onto the publications, I think Vulavakayala Siva has all these 4 papers have been mentioned there. So if you're interested, you can directly refer them. All these things are there somewhere included in these papers, so you can quickly refer them.
Thank you, sir. There's one question is from the Archana Maurya. She has asked that there is any power converter available for a load frequency control of hybrid grid incorporating EV, not using conventional PI/PID controller.
Any power converter available for load frequency control? Load frequency control. That means on the load side of hybrid grid. It seems it's your research problem. You want to ask me about your research problem. Okay, fine. For load frequency control of hybrid grid, it's a long topic. I'm just trying to understand these so many. Incorporating EV, not using conventional PI. Look, to be honest with you, we generally make use of the PI controller most of the time. At most, what we have figured out is adaptive PI are the best solutions. If you are working with the controllers, okay, recently we started with some feed-forward kind of neural network controllers in certain application where we are trying to meet the shading effects. But in most of the other cases, we are simply making use of adaptive PIs. So there may be a number of fuzzy or other kind of controller that may be applied there. but since I directly don't get involved in it, so on the controller side, I may not be the right person to answer it, whether people are using, not using conventional PI/PID controller. Because I don't look into those controller related aspects so much. So any converter available for load frequency control of hybrid grid. So yes, so you have number of converters that actually are there. And I think the simplest solution can be you can have some back-to-back connected converters. I'll not say that directly jump onto matrix converter because we need to explore it before saying like that. But certainly back-to-back converters may be quite useful in these kind of application, and that is already established one. So from the converter side, these are available, but there may be controllers which people have reported. But personally, I feel that adaptive PIs are the best one. They are quick to implement and they work quite well.
Thank you, sir. I think there are no more question. And one more question is there.
Can you explain how the grid disturbances were generated? Okay, so I hope your question is more related with the experimental work rather than simulation, because in simulation you can create it more easily. For the experimental work, we created that kind of grid disturbance by making use of some programmable AC controller. So that programmable AC power supply allows us to create some sort of unbalance in the voltage for a shorter duration of time. So that's how we could get it done in our lab. So there are programmable AC power supplies. Yeah. Or if we are using some sort of real-time emulators also, you can get a feel through the real-time emulators like Opal RT or some other kind of RTs. And then you can make use of some sort of DSpace, etc., to convert it or connect it with the real world. So, but then it's not a very straightforward solution. There is one more question, I think. Can cyclocontroller be implemented in the grid? Cyclocontroller. When you refer to cyclocontroller, I think you are talking about cycloconverters, if I'm correct. I think cyclocontrollers is same as cycloconverters. So yeah, so cycloconverters, okay, they were there and they are still there in very limited applications, because most of the cycloconverters were based on thyristors. And with thyristors, we know the issues are with the switching speed and controlling these devices. You need current controlled gate drives. So that made it more challenging to handle such kind of converters. And therefore, these back-to-back connected IGBTs and these solutions have actually picked up a lot. So I think theoretically, yes, you can make use of cycloconverters, but practically you are going to make the system more complicated and even more kind of large in size. That's my own opinion. Is there any other question?
Maybe, sir, there is no query.
Okay. Yes, Navdeep ji.
कोई query तो है नहीं, sir. और thank you, sir. for
Okay, great.
giving a full lecture. It is for a researcher and they are interested to work on a power electronics converter. So thank you, sir.
Okay. Okay, thank you so much. Thank you for giving me the opportunity to just interact
Yes, sir.
with you all. Thank you.
Okay. Thank you, sir.
Okay.
Good night, sir.
Good night. Good night. I'm leaving now. Huh? Okay.
Okay, sir.
Okay. Bye. Bye.
Yeah. Thank you, participant. Next session will be started tomorrow on the same time, 6 p.m. So good night for all of you. Thank you. You can leave now at the time. Feedback and attendance is also in a chat box. If anyone are not giving, then fill the attendance and feedback through this Google Sheet form. Thank you.